Thank you. Well, thank you for coming today. I am a neurosurgeon. I'm not a geneticist, but I hope this is coherent. I did my part. This team science works, hopefully, and I'm just part of a team here. And so I want to talk about a paper we wrote recently, Inheritance of a Small Posterior Fossa, Trait in 2 families affected by Chiari 1 malformation. This was a collaboration with Dr. Enver Bogdanov, and you can see him at the beginning of the collaboration outside his hospital in Kazan, Tatarstan Republic, Russia. All right, so in this paper we had Anthony Newsoff, who was a very talented postdoc. He was the first author, and the outline of my talk, I'm going to talk about the background. Bogdanov contacted us. He said he found a high prevalence of Chiari 1 in this village, and I'll show you where it's at in Russia. And then we collaborated with Joan Bailey Wilson, who's a statistical geneticist at Human Genome Research Institute. She agreed to be our geneticist. So our method was we were going to phenotype people as either having Chiari or small posterior fossa. Then we're going to conduct linkage analysis. That's where I handed over the football. Let her do that. And then we had, they came out with results of linkage, and they found it in 2 families. We published it, so I'm going to go through the specifics here. A lot of this work started with Tom Millerot and Marcy Spears' work when they published in 1999 the inheritance of Chiari 1 malformation in some families. Except for a few families, the Chiari trait was only inherited through 1 generation. And so in the U.S., even though you do have some people who are affected, generally the pedigrees are quite small. And as you know, if something's not inherited from generation to generation, it could just be environmental. All right, so here's Dr. Bogdanov down there, and he's the guy that called us. And first thing I said when he, emailed us is, "Where's Kazan?" And so it's in Tatarstan. That's where the Tatars live. And so the Baltisy district, that was one small area in Kazan where we had a very high prevalence of patients with Syringomyelia, because that's what over there, that's what they're mostly interested in, is the loss of pain and temperature sensation and the weakness in the hands, because a lot of the people work as farmers and they couldn't do their work. So, and he also identified that it occurred in the Tatars, that's an ethnic group, and not in the ethnic Russians. So he also pointed that out. So we thought so I said, well, we're interested. So we went over there, and so I've had 3 trips to Kazan. I haven't progressed very rapidly, but we finally got the paper published, but had a lot of fun on the way. So went over there, and we here are two brothers. I can't show their faces because of confidentiality, but you can see this one had it longer, Syringomyelia longer, because he had scoliosis, and you would just see things you'd not see in the U.S. Like you could see the claw hand and painless burns and things like that you really don't see in the U.S. anymore. So they're tough people, they're not going to have surgery. He could still work, so it's like, well, why should I have surgery? And then here we're going to one of the clinics, and there went in November. It's pretty far north, so I got caught in a snowstorm, and then I centrifuged some DNA in a HIV clinic. That's the only place that had a centrifuge in this town of 1.1 million. And the centrifuge didn't fit the tubes very well, so I had to throw in some foam rubber. So, but we made it work, and I brought the DNA back in my shoe. Okay. So anyways, made it through customs. So anyways, there are good reasons to do Chiari 1 genetics research in Russia, because according to what Bogdanov told us, and we saw this, there was an area where Chiari malformation had a regional prevalence of about 100 times that of the U.S. And in his population, it was mostly underdevelopment of the posterior fossa. So it's a geographically isolated population. In other words, if you're in a village, people don't move away, so they probably have a common ancestor. That makes it more likely to find a gene for the condition. And as I said, it occurred in the Tatars, not in the ethnic Russians, so it sounded like it had a genetic rather than an environmental effect. So our objective was to find a linkage between the Chiari or small posterior fossa phenotype and a place on the genetic map. And once we mapped it, then after that, we haven't done this yet, sequence the area around the linkage. So we had 52 individuals from 7 families. They're all from Russia. We also had some US families, but we didn't find any linkage in them. All right. So for the small posterior fossa phenotype, not all of the patients had SBGR MRI scans, so we measured the posterior fossa, and we had this measurement. This was a protocol. You have to take special measures when you have foreign protocols. All the protocol consent documents were translated into Russian. So this was our criteria for small posterior fossa, and the patients who had the SBGR scans, we used less than 15% posterior fossa volume compared to supratentorial volume. And we used software to erode away the skull and to just get the volume of the brain here. All right. So then for genotyping, we got 20 mLs of blood. That's how they got DNA when we started the study. Now you do a cheek swab probably. Quality control, the geneticist did that, and then the final data set had the linkage and studies there. All right, as I said, we measured the posterior fossa, and then we converted that to either affected or non-affected. In other words, small posterior fossa or not small posterior fossa, Chiari or not Chiari. And then we performed a linkage analysis. We measured the clivus, the basi-occiput, and the suboccipital bone. The reason we had that OR measurement is in some patients it's hard to find the synchondrosis to measure the length of the basi-occiput. All right, well here were our pedigrees. It says Chiari, but this is really the small posterior fossa. And so you can see that Chiari goes from one generation to another. Here it goes from this generation to another. It looks, in some cases, it looks like it's a dominantly inherited trait. Okay, so what's linkage analysis? Caitlin told me she doesn't understand the genetics, so I thought I'd go through that. Basically, it's because, and I'll show this later. So you have mom and dad, right? And they contribute chromosomes, one each, and then it's this crossover of the chromosomes. So you don't end up basically with just one chromosome from each parent. They cross over. You do get one chromosome, but you can get some from the other one too. And so it's this crossover. And the mapping, what that does is because it's harder to have a crossover between two very closely related points compared to two disparate places, that the closer, the less something recombines, that the closer the genes are and the markers are on the chromosome. So here you go, you end up with your baby, and that's, you just pick it up at the hospital. Okay, so, let me just summarize it basically. If, say for example, in this, the purple is the Chiari, you just try to follow, if the gene goes with the Chiari, then it's linked to the Chiari. And it's more likely to be related to a gene that causes Chiari. All right. So I'm going to show you linkage between some of the variants, the SNPs, and we're also going to have some gene-based linkage here between the posterior fossa and the small posterior fossa and the chromosomal loci. We use this. Autosomal dominant mode of inheritance was assumed. Disease allele frequency of 1%, 80% penetrance for carriers, no phenocopies. And here's our results. So when we looked at all the families on here are all the autosomes, all the chromosomes, not the sex chromosomes. But you can see when you get a LOD score, which is the logarithm of odds, and if it's over 3, generally that means that it's significant. A logarithm of 3 is 1 in 1,000, so that would occur in less than 1 in 1,000 cases. So you see that all these other genes, or all these other markers, are much less than that. But here's one, here's what they call a hit. So on chromosome 1, Q is the long chromosome, 43 location. And then that's a variant-based and gene-based. It's the LOD score is over 3 again. So that looks very promising there. Once you get over 3, generally you can publish. And family 4, okay, so then continuing on family 4, wait a second. Okay, so now we're going to, that was all the chromosomes. Here's family 4. You can see LOD score above 3, 1Q, and here's the fine mapping, and here are the genes of interest. Now, we have markers. They were large areas of interest, of linkage. So these are candidate genes. They're not, we can't say these genes are involved, but all these genes could be involved with bone metabolism, like in the histone methyltransferase, that would be DNA production and then translation, cell proliferation, differentiation, cytochrome oxidase, centrosomal protein. Okay, and then we also found linkage in family 22, but at a different chromosome. This one was chromosome 12. 2.4 LOD score was not as high there. And here's variant-based, and here's some of the genes of interest. This one was sort of interesting. TMEM119 involved in bone formation and mineralization. That sounds very promising. Here's a DNA damage repair gene. Here's an actin binding. That would be connective tissue. So here we are again. We'll get back to the pedigrees, and you can see that we found the linkage, and it seemed like each family had a different chromosomal locus that was involved with Chiari. So the ongoing steps is we have to really find out, we'll have to do even finer linkage to try to find what specific genes are in those regions that we found that seems to be causing Chiari in these families. The families are very interested, they're saying, oh, why is my family affected by Chiari? So it's not sporadic over there. It seems like it runs in the family. So we're going to look at candidate genes, and it's involved in the bone development process. So anything here could be involved. This would be the gene that was involved, say, with achondroplasia, but it's not. They found that gene already, but it will be some gene that's involved in the bone manufacturing process. All right, so in conclusion, we found linkage. We haven't found genes yet. We're looking for the candidate genes. We're going to try to find them, and if they're unknown genes, we're going to have to go in the laboratory, put them in some animal model, and see what the mutations do in those genes, and see what the effects are. All right, there's our team. So thank you very much. Okay.
Questions for Dr. Heiss?
Yeah, Fraser.
So, There was a factor of sort of high penetrance in those families that enabled you to find the gene so quickly. I mean, that was an extraordinary thing to find, you know, to be right on the path so quickly. So,
Well, they're the statistical geneticists, they do simulations before you start. And so with so many people affected by Chiari in that one region, you have a much higher chance of finding a gene than like in the US where it happens sporadically. And few people are related who have it. And the other thing is that people now, I mean, we would like to say, hey, nobody move away, but now everybody's moving away, so probably there's going to be a lot more mixing of the genetic material, and maybe future generations will have less Chiari. But but people want to move away from their small towns. even there.
Other questions?
Okay. All right. Thank you.